All right. Once you define numbers, then you define rules on how to use them. But what are all the different types of number systems throughout history? And that's what we're going to talk about today. We're going to look at most of these. The Babylonians, the Egyptians, the Mayans, the Romans, the Hindu, Arabic. We're going to look at how those are used, because those are precursors to what we use today. First thing we look at are the when we first started looking at numbers, counting things, we used a system called the tally numeration system. For each element that you see, you would simply put a hash mark. And then you count how many you have. But if you have a lot of them, that just becomes a very tedious on how to sort them and determine how many you have. So what they started doing was after every fifth one, you would draw a diagonal line. So we have 1, 2, 3, 4, 5. So that would represent that. So all we have left is 1, 2, 3. So it's much easier. You have 5 plus 3 equals 8 total. So that's what we started doing in the old days. But the more complex the society becomes, the more technologically advanced, the more commerce it has to start developing a number system of its own. The Egyptians, instead of using the hash marks, they represent it as symbols. Remember, the Egyptians had something called hieroglyphics, hieroglyphic or cuneiform type writings, where they took pictures to represent words. Instead of writing them out, they put pictures. So instead of 10 hash marks, 4, 5, 6, 7, 8, 9, 10, they put an N. So as you see from your sheet, there are pictures. So each picture, so a single staff represented one number. The heel bone, which is the N, that represents 10. The scroll represents 100. The lotus flower, the finger, and all these other ones. It represented numeric values. So, as we see in our example sheets, we have the numbers, and here's our number. So let's convert that using this template. So the polywog, which is that first symbol, it represents 100,000. So we have 100,000. Then we have 3 scrolls. Each scroll is worth 100. Those are those 3. Then we had 2 heel bones. Heel bones counted as 10. And you had 2 staffs. Then you'd add them up. You'd have 100,000. There's 300s, 2 10s, and 2 1s. Add those all together, you get 100,322. That's our number, what it represents today. So instead of using pictures, instead of using actual numbers, we use these pictures that repeat themselves. So the Egyptians and the Saudi Arabians back in that part of history, they developed a process, a property called the additive property. Where each symbol, you would add the value of it and get the actual value of what it means. That was pretty good. Jump forward another couple of thousand years, we look at the Babylonian number system. The Babylonians, they were pretty much limited. They said the simplistic form that they had. They only had 2 symbols. At first, they only had 2 symbols. The downward arrow, which is a 1, and the left arrow is a 10. So, for example, in this one here, what would it represent? Well, we have there's 2 of those, so it's 2 times 10, and there's 3 1s. So it's 20 plus 3 is 23. But numbers become bigger than that. The population of the Babylonian Empire, the amount of commerce they have. If you notice, the difference between this number and this number is what? Nope. The space. The space is a very important indicator because now this set of numbers is much different than these. So, for example, in these, once there's a space, okay, these are all multiplied by 1. These are now multiplied by 60. So what we have here, we have 2 times 1, but they're times 60 because they're in the second bound. Plus 2 times 10 times 1 because they're in the first bound. So 2 times 60 is what? 2 times 10. But that had limitations to it. That had limitations to it. Because now, because these are in the next realm of numbers, it's no longer 2 times 1. It's the 60s. And the next one is 60 times 60. Then the next one will be 60 times 60 times 60. So it magnifies itself. Okay, now you'll see a lot of these systems we use are in the multiples of 60. If you think why is that's the reason we still have hours and minutes is based on that 60, the rotation of the earth, because 12 is a basis of all moving systems.
Is that how exponents started?
Yes, these right here, because what happened here, then if we had some more numbers here, let's say we have that, then that, what we would call 60 times 60 was 60 squared. That would be, because yeah, eventually got to a point where it's too many 60 times 60, so I said it's right up here as the exponent. Right. Very good idea. So let's look at these. Let's convert these. What do these represent?
Times
So it's 2 times 10 times what?
60.
Times 60 plus,
1.
well, 1 times 1 happened one time. So we have 10 times 2 is 20. 20 times 60. 1 times 1 times 1. So what is 20 times 60?
1,200.
Right. Whenever you have numbers that end in 0, multiply the numbers. 6 times 2 is 12. And just put the number of zeros behind it. So 6 times 2 is 12 with 2 zeros behind it. And then you add the 1. So it's 1,201. Now the next one. Look at this. But now look at, we have 3 sets of numbers. So how would you write this first one? What does this represent? You have your sheet in front of you, it has a template. Not 10 times 1. It's 10 plus 1. So it's 11. How many times is it multiplied? It's 60 times 60. Because it's in the third category. So it's 10 plus 1 is 11 times 60 times 60. Same thing here. We have 10 plus 1 is 11. It occurs times 60, then plus 1. So what is 60 times 60?
3,600.
36 with 2 zeros. 6 times 6 is 36 with 2 zeros. Then we have 11 times 60. So 11 times 36. 396. With 2 zeros behind it. 11 times 60 is 66 with a 0 behind it. Plus 1. So we have 39,600 plus 660, which makes it 4,000 or 40,260 plus 1 is 40,261. About this last one, this third one. How would you write this one?
1 times 60 times 60 times 60.
Yes, right. 60 times 60 times 60. This is where you would introduce exponents because once you get so far. And the next one would be 10 plus 1 is 11. 60 times 60. It's, well, there's 1, 2, 3, 60, 60. Yeah, that's 260s. And then we have 11 times 60 plus 1. We know this one already, because this one is the same as the one we just did. So that's 40,261. We just have to do this first one. So 6 times 6 is 36. 36 times 6. 6. 216 with 3 zeros behind it. So this one, 6 times 6 is 36. 36 times 6 is 216 with 3 zeros. So now we take this number and add it to our 40,000, which is 216,000. 40,261 is 25,000 or 256,261. Why do you think they need numbers this big? That's one. You have a lot of stuff to trade. What's that? Money, yeah. Population, the census, the thing keeping track of how many people. Because now remember, every society ever since the beginning of time pretty much had taxes. You had to pay for the place you live, and that's how they figure out. Okay, this is how many people we have. This is how much money we get. This is how much we should be getting. Now, the introduction of placeholders. They introduced the placeholder with those two arrows that are pointing up. So what would that represent? What would this number represent? This number is the first, skip this space, and so it's the third location. So it's 10 times 60 times 60. That's this first number. There's nothing in the middle one. Then we had 21 times 1. 6 times 6 is 36 with 3 zeros behind it, plus 0, plus 21, 36,021. So that's what the placeholder. It says that there's no number there. Because I really didn't have a number for 0. That's what that represents, 0. Here's the part that's also very tricky. If you ever study world history, Egypt, Babylon, they're towards the Middle East. What did the rest of the world do? What did China do? What did Japan do? What did the Mayans? Where did the Mayans live? The Aztec, Incas, and Mayans, where do they live? All the way down America, North, Central, and South America. All of this was theirs. Yeah, they had their own numeric system. They developed the most accurate star map ever. This is before computers, before anything else. They developed their stone tablet where you could tell where all the galaxies are, all the solar systems are, all the constellations are, and the planets. So the next thing we're going to look at is the Mayan system. In the Mayan system, we used these numbers: the shell, the dot, and the bar. So what do you think this first number here would mean?
14.
How many bars are there?
Oh,
Yeah, so it's 3 times 5 plus 4 is 19. The shell with a dot over it, because we can keep on adding all the fives you want to, but that becomes very cumbersome. So this is how they introduced the number 20. So the shell that has nothing on it represents what? 0. What would the top one represent? This one here? No, I'm looking at these right here. That's what the equal sign is. 3 times 5, but yeah, so it's 15. So it's 16. But remember, now they go in, this system goes in the 20s. So the first one, these are the ones, these are the 20s. So it's 16 times 20, which is what? What's 16 times 2? 32. And then put a 0 behind it. So it's 320. And then the next number is 0. When you add them together, you get 320. So the Mayans used the vertical stacking method. The Egyptians and Babylonians, they used a horizontal method. So what would this number represent when we stack them?
oh. 13 times 20.
13 times 20, which is what?
260.
What's the one in the bottom?
11
Times,
1.
which is 11. So you get 271. Very good. Like the Babylonians, the more numbers you have, so like this one here, this is times 1. This number is times 20. This number is times 20. Times 20. No. The Mayans changed it. Instead of 20 and 20, they go 20, 18. That's why I put this here for y'all. You see the pattern forming. The more the more numbers you have in your stack. The first one is the 1. The second one is multiplied by 20. The third one is multiplied by 20 times 18. The next one is 20, 20, and keep on going. You're still building up from there on out. Each stack you multiply another number to it.
Next one would have been
20, 18, 20, 20. The next one will be 20, 18, 20. The next one above that would be 20, 18, 20, 20. 20, 18, 20, 20, 20. 20, 18, I mean. You can repeat this pattern. So the next one would be 20, 20, 20, 18. 20, 20, 20, 20, 18. 20. So you always add one more 20 each round. So what's this number going to represent? So that equals 9. This one is 12. 12 times 20 is 240. And this next one.
6.
So 20 times 18 is
360.
360 times 6. So 20 times 18 is 360. 360 times 6 is 2160. And then you add them all up. And what do you get?
3,409.
2409. Because it's 2160 plus 240. That is 2400. These two are 2400 plus 9. All right, so do this next one. Tell me the final number. So this first number is what? 2 times 1 is 2. Next number is, what's that represent?
0.
0. 0 times 20 is 0. And the last one?
10 times 20 times 18 is
Which is what? 20 times 18 is?
3,600
uh,
or 360.
360 times 10. So if we add these all together, we get what?
3,602.
Now, remember I said earlier about the Babylonians, they had theirs at 60s, same as a clock. 20 times 18 is 36. 360 degrees is a complete circle. So that's what they had. Everything is designed that way. All these numbers are basis of 12s. So let's jump up a couple thousand more years. Remember the Mayans, Incas, and Aztecs were around as long, if not longer, than the Babylonians and the Egyptians. And then so were the Chinese and Japanese and that part of the world. They were even further ahead than, but we just study Western civilization. So we start European history. That's what we live by. That's where we came from, which is a shame. If we studied the Central America history and the Asian history, we'd be much further ahead. Then we jump to the Roman numeral system. This is what we still use today. Not every day, but if you watch the last Super Bowl, what was the last Super Bowl we watched?
59.
It was 59. Let's see. If it was 59, remember what it was, the advertisement, what was on there when they flashed it up, and what symbols on the football? That's 59. This is how. Now, up until now, all of this, the numeric systems dealt with multiplication and addition. We're missing subtraction. This is where the Romans contributed. In the Roman numerical system, The numbers are written larger number going down. But if a smaller number is in front of a larger number, then subtract it. For example, what number does that represent?
2025.
Yep. This is our current year. Because it's always the bigger number in front of the smaller number. Let's look at the Super Bowl. So what this says is M is what? 1,000 plus another 1,000. What's an X? 10 plus another 10 plus a 5. So it's just addition property. Or we could use multiplication. We have 2 times 1,000 plus 2 times 10 plus 1 times 5. Same thing. Because what is addition and how are addition and multiplication related?
Same number.
Multiple times, right? Multiplication is turbo addition. It just does addition much faster. And we'll talk about that in this chapter. So, but now let's look at the Super Bowl. L represents 50. But I is smaller than X. It's 1 smaller than 10. So it's 10 minus 1. This is addition. So we have 50 plus 9 is 59. So whenever you have a smaller number, you subtract that value from the bigger one. What did it used to be before it became 2000? How would you write 1900? How would you write 1900?
M, D, and 4 C's.
Nope.
Would it be MCM?
MCM. Because M is 1,000. C is 100, century. So, but it comes before, so 100 from 1,000 is 900. So this number here represents 900. It's 100 before. Now, C, M, the Roman numeral system is based on tens. It's what they use metric systems on nowadays. C, centi. Another name for a penny is what? If you have 1 penny, you have how much money? 1 cent. A cent is 1/100th. So that's why if you have 100 pennies, you have $1. Dimes, so it's a D. So what that says, if you have 10 dimes, you have $1. It goes to the next level. M, milli, which means 1,000. So tell me these two numbers.
Thousand six hundred sixty-six.
Very good. But let me first go over this one. So the M is 1,000. D is 500. C is 100. L is 50. X is 10. V is 5 and 1. If you add up all those, you get 1,666. Now the next number, we have three C's, which are 100 times 3. Then we have 10 happens twice. Then we have a 5. Then we have 3 ones. So that's 300 plus 20 plus 5 plus 3. So it's 325 plus 3 is 28. Okay, now somebody from that side of the room. Do the rest of these. Six, very good, because it's 5 plus 1. How about this one? Right, because it's 5 minus 1. How about this one? Yeah, because this is a 10. This is how you could look at it. It's 10. What does C represent? C represents 100. So it's 10 before 100 is 90. That's one way you can look at it. Plus 1 is 91. And this is a 1 before a 10 before. So how would you read this one? Well, this is a C is 100, right? This is a 9. So it's 9 before 100, which is what? 91. L represents 50. And we have 3 10s, which is 30. And then IX is a 9, with 1 before 10. So it's 89. And then 10 before 100 is 90. Pretty easy, huh? So actually, let's do these face value ones. What's the first one? Because it's 5 minus 1. This one is 10 minus 1 is 9. $50 minus 10 is 40. 100 minus 10 is 90. 500 minus 100 is 400. And 1000 minus 100 equals 900. So far, so good. Now we also introduce a multiplicative property. Like the Egyptians, like the Mayans, they stack theirs, you multiply by a certain. But the Romans had a more convenient way of doing it. This bar means you multiply by 1,000. Because remember, everything in the Roman numeral system is based on tens. So since we want something huge, we multiply by 1,000. So this first one would be what?
5,000.
Yeah, so it's 5 times 1,000, which is 5,000. How about this one? You first have to find this number and then multiply that by 1,000. What is CDX? 410 times 1,000, which is 410 with 3 more zeros behind it. What do you think this one's going to be? What's V represent?
5.
And how many bars above it? So we multiply. So that one's going to be 5 times 1 times 1 is 5 with 6 zeros behind it. So it's 5 million. This one here should have three lines on it also, but for some reason, whenever you had 2 lines close to each other, it combined them. So what would that one be? What's CXI?
111.
111 times 1,000 times 1,000 times 1,000. So it's 111 with 9 zeros behind it.
All of this.
And the last one. So notice in this one, the bar isn't all over all of them. It's only over the C and the X. So what is C and X? So it's 110 times 1,000 plus 1. So it's 110 with 3 zeros behind it, plus 1, 110, 001. That would be that number. You have to be very careful of where that line ends, which is why we look at this next one here. You can combine these properties. So what would this number, what would this answer become? So,
$100,159.
oh, it's very figure it out. What is D?
500.
It has a bar over it, so it's times 1,000. C is what? L is
50.
then IX. So we have 500,000. These three will become 159. So it's 500,159. If you ever watch movies and you see what the copyright year is, that's usually always given in Roman numerals. So that's, you just look at those and you can tell. If you ever go on trips into Washington, DC, a lot of the statues will have Roman numerals. If you ever get a chance to go to Europe, all the numbers are written in Roman numerals. Then we get to our system of numbers, the Hindu Arabic, which are numbers 0 through 9. The Hindu Arabic number system. Why did they use numbers for 0 through 9? How many numbers are there between 0 and 9?
So
7.
Zero.
0, 1, 2, 3, 4, 5, 6, 7, 8, 9. They're not 10 numbers. If you think about it, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What comes after 9? 10. How are we written 10? 1, 0. Then it's 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 7, 1, 8, 1, 9. After 19, we get 20. And then after that's 30.
Much more than this.
Well, no, that's what I'm getting to is, I forget the numbers, is look at this, always look for a pattern. I mean, yes, anybody can count to 1,000, that's not a problem. But what's the pattern here? The first digit tells you which set. This is your original set, then we're one set down. Then we're second set, third set. After we reach 999, what happens? We now go to the 10th set. We start with 0 and go on all the way until we have 999. And then what is after 999? It's the 100th set, which is 1,000. But the last digit always goes from 0 to 9. This is what we call a base 10 numeric system. Because the only digits that we have that we can deal with before they change rows is we deal with numbers 0 through 9. So far, so good. What is this called? And what does it represent? Well, yeah, all expressions, yes. But more so, well, A is a number. N is an integer. Well, at this point, we'll only keep it as numbers, whole numbers. So if I had 3, these are called exponents. What it tells us, the exponent, which is this right here, the number of times you multiply the base to itself. This is the base. So 3 to the 5th means 3 times 3 times 3 times 3 times 3. Which is what we're going with a lot of these systems. Well, instead of writing, if I had 2 to the 36, you don't want to write 2 36 times. So it's much easier to write it this way. Throughout this course, we're going to start off discussing the base 10 numeric system, all of our operations. And then I'll show you how we can use other base systems. There's a tribe in Africa that uses base 5. Every computer system that you ever use uses base 2. So base 10 is not the only number system that we live on. The whole egg industry is base 12. So how many you have 12 eggs in a carton. And we'll look at how those are operated on. So how would you teach your students about number systems? What would you use and how would you do it?
I guess using fingers.
But you're done. You're done after 10. You're done.
I would try to use physical objects.
Like what?
I would use a pencil, but
You can, but you need, how would you get to 60? Remember, if you have 20 students in a class, yes, we have to use blocks. Use manipulatives. In this case, blocks, the number blocks. Have you all remember how to use those? So in number blocks, what do you start with? Start with a single. Okay, now why do they call it 1 unit? One object, yeah. And until you give it a name, because what if it's a penny? Then it's 1 penny. If it's flowers, it's 1 flower. So we use this as a generic term to be anything any object we're using from there on out. It's base 10. So once we have 10 of these, 4, 6, 7, 8, 9, 10. This equals 1 long. Yeah, we'll get there. We'll get there. Now, look how this is built. We have 10 individual blocks. That makes 1 long one. So if you have, that way, you don't need to have 10 small blocks. You just have 1 long one. What happens when you take these longs and you put them together? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 longs. This equals, because we think about it, if it's just 10 of these things right here, it's 1 flat sheet. So we call it 1 flat. How many blocks are in 1 flat?
100.
Yeah, because there's 10 of these, and there's 10 units in each one. So 10 times 10 equals 100 units. Now we take these 10 flats and put them together. There's 10 of these flats. So you have 10 flats. Each flat has 10 rows. This equals 1 block. How many units, single units are in there? 1,000. Because we have 10 times 100. Because each of these flats have 100 units in it. So you see, just by doing this, you're teaching your kids what operations? Addition and what else? And multiplication, exactly. Just by playing with these, you have just now introduced those two concepts to them. What can you teach from there on out? Subtraction we can, but before we do subtraction, what do you teach first? My wife is doing research right now in that when you're in elementary school, what are all the songs that the kids sing? Give me the first song that pops in your head.
Yankee Doodle.
Okay, is there any math in there? No. ABC, no math in there. So what songs deal with numbers and math in elementary school?
99 bottles.
Ah, okay. I don't think you want to teach them 99 bottles. What it is, it's 10 monkeys jumping on a bed. What do you think? But now what operation is that? Subtraction. Why do we insist on teaching addition first when all the songs are subtraction? I can't think of any songs that elementary school kids sing that are addition. It's always one fell off 99 bottles or stuff like that. It's always subtraction. So she's researching now. If we start that off, would it be easier for the kids to learn mathematics? Because we teach them addition, we sing songs of subtraction, we get everybody confused. So that's another story there. How would you teach them addition? Using blocks. There's nothing to break apart.
Give them 8
Well, yeah, the first thing you got to do is teach them what these numbers represent. What does 8 mean? Eight units. So have them take out 8. Is it the same as a long already? No. So we can't use it. So we add, which means we make it bigger. We put 3 more to it. So when we do that, we know that we're going to have enough blocks to make a long with 1 left over. So this is 10. This is 1. This is how you introduce the number system to kids. You have to relate it to blocks of some sort. Or if you don't use blocks, use something else. Use erasers, use pieces of paper, whatever. But this is the way you do it. And then you can go even bigger. Once they get comfortable using these and converting them from units, single units to longs, then we can use a bunch of longs. So how would you represent these numbers? What is 23 made up of?
Two longs, three.
Yeah, it's made up of 20 plus 3, which is 2 longs and then 3 units. Plus 1 long and 5 units. So when the kids put those together, they got 3 longs and 8 units. So this is 3 times 10 plus 8 times 1, which is 30 plus 8. And this is how you teach them addition. What else? Oh. The next page on your sheet, these are other base systems. Base number is 1 just by itself. Base number 2, which means we have 2. Base 3, we have 3 elements. So what does this mean? What does this represent? If you're dealing with a base 3 system, that means the most you can have are 3 numbers. So base 10, what are the numbers in there?
0 to 9.
0 through 9. There are 10 numbers. So what do you think a base 5 system would look like?
0 through 4.
0 through 4. A base 3 system? Right. It's always going to be 1 less than that because that 0 is there. And you have to have 0. Why? Well, it's a number. 0 is the absence of any number. You have to have a 0. So we know that 15 plus 26, when we add those, this is base 10. 5 plus 6 is what? So 11. Put this in the ones, put this in the tens, because that's 11. And then we add up all these now. 2 plus 1 plus 1 is plus 41. Mathematically, are we sure that's base 10? Well, you won't know until you tell me these are base 10. Usually you have the word, you can either have like 15 base 10. Because if you're dealing with different base systems, you have to tell me what base you're using. Because these numbers, I can use them for base 7 or base 8, which is give me a whole different answer. Let's look at base 5. Base 5, you have the numbers . How does this relate to what we're dealing with? In a base 10 system, the number 234 is written as 200s, 30, and 4. So this is 2 times 100, 3 times 10, and 4 times 1. Remember, we're looking at base 10 here. What is 100 made up of? 10 times 10, isn't it? This is 10 squared. 30 is made up of 10 to the first power. 1 is made up of 10 to the 0 power. Anything to the 0 power is 1. This is how we can convert, we can determine what that value is. So when we have a number, whatever number we have, it has to fit into our numbers, when we write them out, have to fit in one of these columns. These are our placeholders. 10 to the 0 is 1. 10 to the first is 10. 10 to the second is 100. 10 to the third is 1,000. 10 to the fourth is 10,000. The exponent says how many zeros I have. So the number 2135 is written like this. 2 in the thousands, 1 in the hundreds, 3 in the tens, 5 in the ones. We have to do the same concept now in base 5. In base 5, 5 to the 0, 5 to the 1, 5 to the 2, 5 to the third, 5 to the fourth. They keep on going. So the number this is no longer 13 base 5. 13 is a base 10 number. The way you would read this is 13 base 5. That's what it represents. So the true value in base 10, the conversion of it, what is 5 to the 0 power? What is 5 to the first power? 5 to the second, 5 to the third, and so on and so forth. This is base 5. This is base 10, our conversion. So if we want to convert, what is 13 base 5 in base 10? 3 times 1 is 3. 1 times 5 is 5. Add those. So 13 base 5 is equal to 8 base 10. This is how you convert numbers from one system to another system. So do I put any examples on there? Let's look at this. What is the conversion value? What is it in base 10? What is 3, 4 base 5? So the first thing you have to do is you have to create your template. So since it's base 5, we have 5 to the 0, 5 to the 1, 5 to the 2. This is base 5. This is base 10. 5 to the 0 is 1. 5 to the 1 is 5. 5 squared is 25. 5 cubed is 125. So now we put the numbers 3, 4 inside there. 3 4s here. Now we multiply. 4 times 1 is 4. 3 times 5 is 15. Add them together. So this is 19 base 10. Make sense? Let's go backwards. Let's go backwards. Well, actually, let me give you this one. Tell me what this one would be in base 10. I don't know. Let's find out. I never guess in mathematics. So this is 5 to the 0, 5 to the 1, 5 to the 2, which is 1, 5, 25, which would be 1, 1, 3. There's my number, 1, 1, 3. This is the equivalence. 25 times 1 is 25. 1 times 5 is 5. 3 times 1 is 3. 25 plus 5 is 30. So it's 33 base 10. Let's go backwards. What is 26 base 10 in base 5 numbers? Okay, when you do this, you have to work backwards. 26. Remember, these are base 5s. These are my base 10 numbers. 26. This is too big. So let's see here. We have to make it equal 26. That would be 25 plus 1. So it would be 101 base 5. We want to equal 26. So how can we arrange these? We can take multiple of these. Let's look at 73 base 10 to base 5. Let's do 173 base 10. So we can take away. So we have 173. We can take away 125. But think about this. Well, let's just start with that. So use the largest number first. So we have now 48. Does 25 fit into 48? How many times? One time. Does 5 fit into 23? How many times? Can we use the number 4? Yes, because base 5 goes from 0 to 4. So 4 times 5 is 20. And then it's 3. So the answer is 1143, base 5. And you do the same thing with base 2s. In base 2 numbers, instead of having all these, all you have are 2 to the 0, 2 to the first, 2 to the second, and so on and so forth. And the only numbers you can use here are 1s or 0s. I could put 0 through 4 in any one of these. I can use 0 through 4, but in binary, in base 2, it's only 1s or 0s. For example, 1101 base 2 is what in base 10? So it's 2 to the 0, 2 to the 1, 2 to the second, 2 to the third. 2 to the 0 is what value? 1. 2 to the first, 2. 2 to the second, 2 to the third, 8. So now I got to put 1101 inside there. This is base 10. This is my number. So 8 times 1 is 8. 4 times 1 is 4. 2 times 0 is 0. 1 times 1 is 1. So that equals 13. Base 10. So once you have your columns, put the numbers in there and then see what the conversion is. (27) base 10 to base 2. We have 1, 2, 4, 8, 16. So we have to keep on going until we get a number bigger than that, our answer. We can't use this. So how many times does 16 fit into 27? One time. So 27 minus 16 is 11. Does 8 fit into 11? One time. Does 4 fit into 3? Does 2 fit into 3? Does 1 fit into 1? So my base 2 number is 11011 base 2.
This will be our original, so interpret the numbers between
This is a conversion. You have to be able to convert from base. Yeah, I'm sorry. Yes. You have to be able to convert from base 2 to base 10. Or base 5, or base anything. But this is how you do it. You have to, whatever the base is, start power 1, 0, 1, 2, 3, however, till you get that number. So that does it for the first section. That's how we design systems and computers. It's all base 2. All right, everybody, have a great, safe, remember, no school tomorrow.